I'm Miwako Tsuji from Riken Center of Computational Science. Today I'd like to talk about performance evaluation of A64FX ARM processor using fiber Miniapp suite. So please note that our experiment had been conducted during the early access program of Fugaku. It means that the results can be differ from one obtained in the official operation period. So supercomputer Fugaku has started for operation in this March. It was number 1 of top 500 in June and November last year. It uses A64FX ARM-based processors. So in this presentation, performance evaluation of the A64FX using fiber Miniapp state will be shown. The fiber Miniapp suite is a set of mini applications extracted from real applications. So it is developed by application feasibility study team of Fugaku project. It includes some of the target applications of the supercomputer Fugaku. The results of performance evaluation are available for a wide range of systems such as K-computer, Oculus packs, HF packs, and so on. So in this presentation, we focus on Intel Skylake and ThunderX2, but if you are interested in the result of all other systems, please refer this paper. The A64FX processor is a processor developed by Fujitsu based on ARMv8.2-A Scalable Vector Extension. So supercomputer Fugaku and its consumer version uses this processor. So this is an overview of the node of A64FX. As you can see, it takes NUMA topology. There are 4 NUMA groups in a node. The NUMA group is called CMG core memory group here. A CMG has 12 cores and 1 assistant core dedicated to operation systems. As well as double and single precision, half precision floating point operation is supported. It adopts mVMC, which capacity is 32 GB in total, and the memory bandwidth is 1024 GB per second. So thanks to the Ryzen HC technology of 9 nm, the power efficiency of the A64FX is 50 GB per watt for GGM. This is a detail of CMG of A64FX. There are 2 computation core and 1 assistant core. In a single core, there are 2 512 SIMD floating point units. 2 512-bit SIMD loads or 1 SIMD store can be performed simultaneously. L2 cache of 64 GB is dedicated to each core, and L2 cache of 8 MB is shared by 12 cores. 4 CMGs support cache coherency by CC NUMA with on-chip directory. So there is a memory control of mVMC of 8 GB. So these tables show the comparison of specification of supercomputer Fugaku and K-computer, which had been replaced with the Fugaku. So I will omit the detail of this specification. Since the A64FX adopts many core NUMA architecture, there are some methods to specify the affinity and allocation of thread. So in this presentation, I have used the environmental variable FlibCP affinity. So you can control the affinity by specifying core ID or specifying the period of core ID and its interval. The other environmental variables, such as OMP or GMP, are also available. So NPR process can also be allocated by CMG by using environmental variable called NUMA assign policy. So there are 3 options: simplex, share cyclic, and share band. In case of simplex, the processes are allocated to CMG exclusively. If you specify share cyclic, the processes are allocated to CMG with sharing other processes. The processes are sequentially allocated in different CMG. In case of share band, the processes are sequentially allocated in a same CMG. So this shows the example of thread and process allocations. So in this case, there are 4 MPI processes and 2 OpenMP threads per process. So if allocation policy is simplex, then processes are spawned across different CMG. if you specify the interval of thread 1, 3 continuous physical cores are used in each CMG. This is another example. So here there are 8 MPI processes in a node, and there are 3 OpenMP threads for a process. So if you specify share band for a process allocation policy, then 2 continuous MPI ranks will share a CMG. So in this case, rank 0 and 1 share a CMG, and rank 2 and 3 share another CMG. So if you specify share cyclic instead of share band, then MPI ranks are assigned in cyclic manner, so that rank 0 and 4 share a same CMG, and rank 1 and 5 share another CMG. So in addition, if you specify interval of thread affinity policy 2, then thread allocation leaves a space between 2 threads. Let me introduce Fiber Miniapp suite. Fiber Miniapp suite is a set of mini applications derived from the full-scale applications. The original application had been developed for large-scale systems. The suite covers a wide range of applications in terms of scientific areas and computational characteristics. So for example, CCS-QCD is an application of quantum chromodynamics and compute structure algorithm Monte Carlo. This shows an experimental environment. So I have used 3 systems composed of different processors. So I'll omit the detail of the specification, but please note that whereas a node of A64FX is only single processor, there are 2 processors in case of ThunderX2 and Skylake processors. So basically, all code are compiled as is. And we use general recommended options such as O3 and K-fast. So to compare different systems, the best result over different parameters such as number of threads or number of processors or allocation policies are adapted. So the first example is CCS-QCD. This program benchmarks the performance of linear equation solver with a large-scale coefficient matrix appearing in a lattice QCD problem. This application is known as a memory bound application. So we have tested 2 different sizes of CCS-QCD, class 1 and class 2. So this shows a result of class 1 problem. So in this case, there are only 1 MPI processor. We have varied the number of threads from 1 to 48. Also, we have changed the interval of threads if it is possible. The result shows the flop, so it means that the higher is better. We can see a very good scalability up to all 48 cores. So this is thanks to the environmental variable shown here, which enable us to effective fast touch memory allocation. So this is a result of a larger application class 2 cases. We use 8 or 60 nodes by changing the number of threads per process. So we have tested different process allocation policy, but regarding the MPI process affinity policy, there is not so big difference. So share cyclic is slightly better, but there is not so big difference between 2 allocation policies. In case of 8 node, where 2 MPI processes share a CMG, it overcomes the 16 node case in terms of the performance per a single node. This shows a comparison of 3 systems for 2 problem sizes of CCS-QCD. So please note that in these indexes, the numbers means number of nodes, number of processes, and number of threads. And for the smaller cases, class 1, a single socket of Intel Skylake and ThunderX2 is better than the A64FX. In case of class 2, so while we employed a different number of nodes, but considering the difference of frequency between the A64FX and Skylake, the performance of A64FX and Intel Skylake are comparable. So let me move another application. The FFVC application solves three-dimensional incompressible neighbor stroke equations in even spaced Greek point orthogonal space using finite volume method. So this is also memory bound applications. So this shows a result of two different sizes in A64FX. So again, we have changed the process and thread allocation policies, but there are not so big difference between different policies. And this shows a performance comparison with ThunderX2 and the Skylake in each problem sizes. So especially for the problem size of 1024, A64FX 8 node and 8 sockets, it's 2.7 times better than Skylake of 4 nodes and 8 sockets. So let me move mVMC, which analyzes the physical characteristic of strongly correlated electron systems. So here we consider two sizes of problem, tiny and middle. For tiny case, because this is very small problem, the performance is saturated up to 8 threads. And as you can see in the graph of tiny, in the graph of left-hand side, the performance is affected by the number of interval between MPS threads. And it suggests that close allocation is the best. For MPI, in case of middle problem of 4 node or 8 node, the cyclic gives better results than share band. So that it means that for this application, thread should be close and process should be allocated in cyclic manner. This shows the performance comparison of middle-sized problem. I'll omit the comparison for a tiny size because it is very small and all processes are saturated with a small number of threads. So apparently, the performance of A64FX or middle-sized problem is worse. So according to our performance analysis, there are store fetch interlocks where SIMD load instruction most weights the preceding store instruction over same address. This SFI can occur even if the address is masked and there is no real access by SIMD instructions. And the performance penalty of SFI is unfortunately it is very high in case of the A64FX processor. We consider that this is one of the reasons of the performance degradation of A64FX for this application. So let me move chemical application NTChem. NTChem compute fast principal electronic structure. So the main kernel of this application is dense matrix operation performed by DGEM library. So that the performance of mathematical library are very important for this application. We consider two different sizes, H2O small size and Taxol. And this shows the performance comparison of NTChem for H2O and Taxol. In case of Taxol, the right-hand side graph, the node of A64FX is actually comparable with a node of Skylake, considering the difference of peak performance. Since the performance of DGEM is generally affected by the peak performance, so the result of the Taxol is very reasonable. On the other hand, so in case of H2O problem, which is very small problem, the performance of A64FX is very poor. To investigate the reason, we see the breakdown of execution time of 3 kernels of NTChem. So there are 3 kernels, energy, Tran 2 and Tran 1. And the graph shows the execution time of each kernel. It means that the smaller is better. Apparently, for the H2O problem, A64FX take very long time for Tran 3C1 kernel. So for other kernels, especially energy kernels, the performance of A64FX is comparable with Intel Skylake or better than Skylake. So this is a performance analysis report of the Tran C1 kernel for H2O problem and Taxol. So apparently, for the H2O, the floating point busy rate of the A64FX is very low. So it means that most of the time, the floating point unit idles. So comparing two graphs, there is very long wait time for floating point operation. And also, it have to wait integer load from L1 cache. So this fact means that for a small problem such as H2O, basically it is difficult to schedule interactions by software pipelining or other techniques. So that it is difficult to hide long latency in A64FX interactions. So these two long waiting time of floating point operation and integer load from L1 it also appears in case of CCS class 1 problem, which I had shown as a first example. So let me show some result using auto-thread parallelization of Fujitsu compiler by for NTChem application. So this is a criminal application. So giving k parallel option, Fujitsu compiler will generate select parallel binary even if there is no explicit OpenMP directives. And these show the result of NTChem for different number of threads. So as you can see, even though there are no explicit OpenMP directives, we can observe good scaling up to 4 threads. This is another example without explicit OpenMP directives. So in this case, the performance curve is more moderate than the case of NTChem, but also we can show good scaling up to 4 threads. So this is a summary of my presentation. We have evaluated the performance of A64FX processor using fiber Miniapp suite. We have tried several thread and process allocation policies. Basically, process allocation strategy does not affect the performance in most applications. Thread should be assigned closely for most mini applications. The A64FX processor is not good for small problems such as class 1 of CCSQ-CD or H2O of NTChem. We consider that the reason it is difficult to hide latency by instruction scheduling, so that long latency in the A64 processor appeared. We have observed SFI, store fetch interlock, decrease the performance of mVMC. So because the performance penalty of the FSI is high in the A64FX processor. For other mini apps, the performance of A64FX processor is comparable or better than other processors. Also, we investigate the performance of auto-vectorization, and Fujitsu compiler's auto-vectorization shows a good performance up to 4 thread for NTChem and FFP. So that's all. Thank you.